Hi, my name is Trevor Goldston. I am a senior in the UNC Asheville Mechatronics Engineering program and the team lead for this year's senior design project. I am sharing this condensed presentation as a part of my application for the Tesla Manufacturing Development Engineering role. This is an overview based on our senior design work from the first semester, where we were tasked with designing an autonomous ground robot and drone for the Institute of Electrical and Electronics Engineers, or IEEE, student hardware competition.
So I'm going to start with showing you an animation of this year's game. This year's competition will be on a 4-foot by 8-foot game board. The board is divided into 4 zones. Zone 1, Zone 2, Zone 3, and Zone 4 in the middle is the crater. Attached is the Earth structure. There is a green start area and a blue lunar landing area. Attached to the board are 4 antennas. Scattered randomly across the board are 5 astroducts. There is also a 6th astroduct in the crater. Above the star area are 2 white star LEDs. When these turn on, it begins the round. When the round begins, your bot must start within a 12-inch by 12-inch by 12-inch cube. Once it leaves the star area, it can expand outside that volume. Every team will consist of a base bot and a drone, and it must complete the following tasks. It must collect all the astroducts from around the board and return them to the lunar landing area. It must go to the first antenna and press its button 3 times. When it does this, it will initialize a random LED color at the top of the antenna dish. It must proceed to the next antenna and type in code 73738 pounds, where another random LED color will appear at the top of the dish. For the third antenna, it must return the astroduct off of the pressure plate to the lunar landing area. And on the final antenna, it must rotate a knob 360 degrees. Your basebot must then launch the drone to start reading antenna LED colors. Then the basebot must enter the crater, do a full lap around the crater, and exit the crater. The basebot must then return back to the start area, and the drone must then report all the antenna LED colors to the Earth. The drone must then land back on your base spot, and that completes the round. So now that you have a better understanding of the competition, I wanted to explore the design of our team's bot. So typically in these competitions, teams use multi-directional wheeled robots because they can move freely in any direction. However, those designs work best for flat surfaces and would lose traction at the bottom of our crater while exiting. So one of our main requirements was to find a design that could still give us omnidirectional movement around the board, but also enable us to traverse steep terrain and enter and exit the crater. So we ended up taking inspiration from NASA's Perseverance and Curiosity Mars rovers. As you can see in these two pictures, you'll notice this strange looking suspension. This is called a rocker bogie. And on first glance, it looks a bit complicated. So on the next slide, we'll break down why it's so useful and robust. So the key idea here is that there are no springs or shocks. The system relies entirely on geometry to distribute loads mechanically, keeping all the wheels on the ground, maximizing traction, and allowing the main body to stay relatively level with little vertical motion. And as we can see in the second image, we can also motorize each joint at each wheel so that every wheel can steer independently. And this gives us the ability to move in any direction around the board, traverse over obstacles, and maneuver around steep terrain. So running with this idea, we first ran some rough SolidWorks simulations to tune our geometry while staying within the constraints of the competition. After a few weeks of iteration, we were able to build our first working prototype, and as you can see, we were able to successfully enter and exit the crater. Once we had a good idea of what our chassis would look like, we started looking at how are we going to activate each antenna. We began with the rotary knob antenna, which, as you can see, is on the far side of the board. And one of the challenges we faced is that the further we get from the start area, the more our navigation error can grow. So we needed a way to engage the antenna, even if our bot's position was slightly off in orientation. That's when we came up with the simple like L bracket idea. Uh, we attached this L bracket to a motor. And even though it looks simple, it ended up being one of the most robust antenna engagement systems on our entire bot. It can be off by several millimeters in the normal direction, meaning too close or too far from the face of the antenna. It can be off in the horizontal direction, meaning too far to the left or right of the antenna. It can even tolerate quite a bit of angular error. And most importantly, it can work for a combination of all three. Next, we focused on an antenna that proved to have a couple of different challenges, the pressure plate antenna. One of the challenges of this task, like the rotary dial earlier, is the distance of the antenna from the start area. But its difficulty is also compounded by the fact that the antenna isn't located on the same plane as the rest of the antennas. Instead, it's located inside the crater. So during the brainstorming process, we decided that one of our key system requirements would be that our robot would not have to drive down into the crater to grab the duck. Instead, it should be able to retrieve the duck from the edge of the crater. To meet that requirement, we took inspiration from the 2024 IEEE team. Their robot designed 4 game pieces into predictable positions where a hard-coded robot could then perform the task. In a similar way, the duck on our antenna will always be sitting on the pressure plate, so its position is also predictable, which made a robotic arm a natural choice for our design. For our first proof of concept, we used VEX motors, gears, and rail from the lab to build a simple working robotic arm. And as you can see, the motion of this arm is pretty choppy, and this helped us realize we needed a better way to control how the arm moves. For our second prototype, the team researched how to derive the forward and inverse kinematics of our arm. Kinematics is a field of math that lets you mathematically describe each joint of the robot and then control the motion of the whole arm in a smoother and more predictable way. As you can see here, we were able to also shrink and lighten the arm by switching to smaller motors, carbon fiber tubing for the links, and 3D printed claws for the ends. With the new kinematics and lighter design, you can see how much smoother this prototype moves compared to the first one. Next, we focused on the keypad antenna, which required us to type in code 73738 pounds. We decided to give each of the required keys, the 7, the 3, the 8, and the pound, its own actuator. We then selected small solenoids that fit within the mechanical envelope of the keypad and fired them in a sequence with about a half a second delay between each key press. With that design in place, here is our current prototype. This design was also beneficial as it served a second purpose. As you may remember, our last antenna is the antenna directly across from the start area, and the task for this station is to press the big red button 3 times. We realized while making the solenoid cluster that its overall size and cross-section were small enough that all 4 solenoid tips could fit inside the 60mm red button, as shown in the cross-section on the right. We realized that if we fired all 4 solenoids at the same time, the cluster would be able to press the button and engage the antenna. In our first prototype, it worked exactly as expected. Now that we've gone through all of our antenna engagement tasks, I want to quickly recap our tools. At this point, we have subsystems that can engage the red button antenna, the keypad antenna, the rotary dial antenna, and the crater duck antenna. And now we wanted to start looking for ways to make these subsystems more reliable in the case that the robot is a little misaligned when it drives up. The pressure plate antenna is a little more complex in this case because it has to go down inside the crater. So for that one, we will have to rely solely on navigation for it to align properly. But for the other antennas, since they are all mounted on the flat playing surface, our base bot can drive straight up to them and physically interact with them. That means we can design those subsystems to have some form of a mechanical advantage to help with alignment. We realized we also needed to approach every antenna from the same side of the robot. That is because we only have one navigation camera on the front of our bot to see the environment. So this raises a big question. How can our robot use all of its tools if it can only approach the antennas from one side? That is when we got inspiration from a previous alumni. He recommended a simple rotary cube system. So if you imagine the cube here, each color on the cube represents a different tool, and the robot can just rotate the cube to whichever tool it needs. So running with that idea, we added the rotary cube to the bottom of our robot. It is fixed to the chassis using a bearing so that it can rotate independently from the rest of the chassis. Then the rotary cube can spin to the correct tool for the keypad or red button antennas, or rotate to the opposite side when we need the rotary antenna tool. But even with this solution, we ran into yet another problem. On our keypad antenna, there needs to be a lot of precision because there's not a lot of room for error. To accurately line up the tips of each solenoid, the robot has to be perfectly centered. If we are misaligned or mispositioned in any way, we could either partially press the buttons, miss the buttons entirely, or even worse, start pressing the wrong buttons. So we needed a way to make sure that we were able to stay square with the antennas every time we approached them. That's when our previous inspiration resurfaced yet again. In his proposal, the rotary cube actually came with a clamping mechanism mounted on the front of the robot. That way we can grab the antenna and straighten ourselves out. And as you can see, it works pretty well. In future iterations, the clamp and the rotary cube will be mounted together on the same bearing we mentioned earlier. This way we can rotate independently of the chassis. And once the clamp grabs the antenna, any misalignment in the orientation of the rotary cube will be corrected. Now that we've gone over the entirety of the base bot, we're going to shift over to the drone. Our drone hardware is made up of a carbon fiber chassis with 4 motors, a flight controller, and an energy-dense battery, and most importantly, a high-resolution camera. Up until this point in the design process, we tried to keep every subsystem as simple as possible. But for the duck collection, we decided to try to do something more ambitious. We wanted to use the drone to collect and identify the ducks around the board using its camera and identify the antenna LED colors. The first challenge we faced with the drone was determining the position of the astroducks. Since they are randomly placed, the drone can't simply go to the same positions on the board every time. The drone needs to be able to see the ducks to determine their location. To achieve this, we trained a computer vision model to recognize the ducks in a variety of environments. Using only about 50 images of the ducks in different orientations, locations, and lighting conditions, we programmed the model to detect key features like the head, the body, and the beak of the ducks. While the drone flies, it uses this model to identify the ducks, and after a series of calculations, the drone can determine the duck's position on the game board. The next problem we had to consider was how to deposit the ducks to score points. Each duck must be entirely within the lunar landing area, which is this blue square. Even if the duck's head is in the blue square, if any part of its body is outside of the lunar landing area, it does not score. This means we needed to organize them so that they fit all neatly inside the space. Ideally, we would deposit them in this grid-like formation, where all the ducks face the same direction as seen here. So we needed a method to detect the orientation of the ducks during pickup and drop-off. We solved this problem by training a computer vision model to calculate each duck's facing angle. We programmed our model to use the relative positions of the duck's head and beak to determine the duck's orientation. Using the setup shown here, we tested our computer vision model's calculations. We placed a duck on a rotary chuck to give the ducks different measured orientation and positioned the camera above the duck where the drone would realistically be during the collection process. To verify that our model worked, we compared the computed facing angle to the duck's true angle in space. The results of this test show that the angle our computer vision model calculated in green is roughly within 3 degrees of the duck's true angle in red. This is more than acceptable for the job. Now that we can identify and locate a duck, we need to be able to pick up a duck. So that's when we started prototyping our biomimicry gripper. We were originally inspired by the MIT soft gripper, where they retracted and released tentacles to grab objects. So after some research, we found a print-and-play soft gripper that we started testing made by a creator named XYZ Aiden. However, this version, while functional, it was too heavy for our drone. Our drone has a 250-gram weight limit in the competition, and this gripper would have pushed us over that limit. So we removed 2 of the arms, made the 2 remaining arms thinner, and added 2 claws at the end to secure the duck's head. This version worked really well. So now that we have a reliable way to grab the ducks with the drone gripper, the last requirement for our drone's camera is that we need to be able to identify the antenna LED colors. And for this, we decided to use a hue, saturation, and value, or HSV color filter. But first, what is HSV? We will use this online color picker to explain. So hue is simply the color itself. In other words, what exactly is the wavelength of light that we are looking at? What color is this on the color wheel exactly? Saturation is how faded the color is. So you may imagine you have a red shirt and you wash it 10, 20, or even 1,000 times, eventually it fades. The color didn't change, it just lost pigmentation. That loss of pigmentation is what saturation describes. Finally, value is the lighting conditions. Are we in direct sunlight, shadow, or is it nighttime? Just because we're in the dark does not mean that the actual color of the object has changed. Value tells you how bright the color appears to be based on the environment. So that is an overall brief explanation of what HSV is. But now you might be wondering, wait, why are we doing all of this stuff with an HSV color filter when we already showed earlier that we can use a simple computer vision model to identify a duck. So why not just keep using that model and just train it instead to identify the colors of each LED? Well, I'll show you why. If I asked an AI model what color is this LED, purple, red, blue, or green, it would probably say red because that is the only blatant, obvious patch of those colors anywhere in the image. But what if I added a green bowl in the background? What if I added a green bowl, a green wall, a red box, a blue recycling bin, purple papers, and a purple bot to the image? At that point, it is very likely that the model would get confused if we asked it the same question again. HSV is special because we can tune it to only look for the purest and brightest versions of each color and how much of that desired color there is. If the background colors do not fall inside that range, they get filtered out and the LED color is all that remains. And as you can see from our trials, it has been able to correctly identify the color of every LED we've tested. But I want to point out two special cases. The first case I want to point out is the red antenna LED. Notice how the system completely ignores the red boxes on the shelf in the background, even though they are clearly visible. Because although the boxes are red, they're not a bright red, so that's why they don't show up in our filter. For the second case, I also want to highlight one more special case on the green antenna LED. If you look at the big red button along the bottom, even though it's a pretty pure red, there is not enough of a concentrated bright red in that area for the filter to consider it a red LED. Also, notice how the three green LEDs also didn't even make it through the filter because they were the wrong shade of green. All of this really shows the strength of using HSV color filter for our application instead of a full computer vision model, which would require much more computational power and electrical power. Now, I want to wrap up the presentation by saying that so far we consider this semester a success because we now have a viable subsystem for every task on the board, and they're working pretty well. Next semester, our goal is to order all the parts, assemble everything, integrate all the subsystems, and have it tuned and tested before competition day. But for now, thank you.